Okay, welcome to the M-Cubed weekly seminar. Today we have our esteemed colleague, Peter Sullivan, giving the seminar. Peter is a Colorado native, born and raised in Pueblo, Colorado. And he took his PhD in civil engineering from Colorado State University, 1984. From 1985 to 91, Peter was an engineer at Boeing Aerodynamic Research, and he spent his time modeling turbulence over wings and transonic flow. And it must have been a lot of fun. In 1991, he came to NCAR, where since 2009, he's been a senior scientist in MMM. He's been the director of NCAR's geophysical turbulence program since 2013. Peter's an expert in large eddy simulation of boundary layer turbulence in the atmosphere and upper ocean, air-sea interactions at small scales. In particular, he's using LES and DNS to study turbulent flow over moving waves, convective and stable boundary layers, stochastic wave breaking, wave current interactions in the upper ocean. His publications were nominated by M-Cubed as Paper of the Year 3 times. And in 2004, he received the UCAR Best Publication Award. He's a frequent participant in field programs, for example, the Horizontal Array Turbulence Study, HATS, to measure subgrid scale variables in the atmospheric surface layer over land and the ocean. He's been a frequent lecturer at summer schools in Italy and France. And I remember the summer school we did together. We flew over at the same time, and I don't think Peter slept for about 3 or 4 days. But his seminars were, you couldn't have known that from his seminars, because they were all top notch. The students really enjoyed them, and so did I. So here, Peter's going to talk today about the impacts of heterogeneous ocean surface on atmospheric marine boundary layers. Peter. I think you went.
Thanks. Oh, thanks, Rich. I remember Rich was the guide when we went to Italy. We're sitting in the air. We're sitting. Oh, really tired. So Rich is there, Gail is there, and we're sitting at the lounge right next to the gate to take us to the southern part of Italy. And the loudspeaker comes over, and they're speaking Italian, and I'm really tired, and I'm not paying attention. And all of a sudden, Rich says, "Oh, they moved our gate to the next concourse." And so I would still be sitting there if it wasn't for Rich translating the Italian. Oh, it was a wild adventure. It was really fun. There's the title of the talk. I was going to use a really cavalier title, what I did during COVID, but I thought that was a little too flip, and so we needed something else. Fellow collaborators, Jim McWilliams, Jeff, Ned Patton, and Joe Fernando at Notre Dame. One of the things is ONR has been very much a supporter of my work over the past, and recently there's 2 DRAs, Mesobob and Calypso. One of the things that they've done, which I greatly appreciate, is I've gotten millions of hours of computer time to run there in the simulations you'll see. Also part of Atomic and that's connected to Eureka. And so thanks go to them. I looked at my talk and I realized, wow, there's way too much to do. So some should be very small letters. And so we're going to take a grand tour. We'll just skip lightly over some things. Hopefully they'll be interesting and not auger into awful detail. Okay, we're going to talk about the atmosphere, but let's start in the ocean. I stole this picture from Jim. If you really want to read a great article, oh, it's so nicely written. Jim from 2016 wrote this review article. It's really fabulous. So Jim sketches out how energy flows in the ocean. There's balanced motions at the large scale, which are pretty well understood. And then at the very far side, in the boundary layer, small scale measurements learned a lot of the detail. The mystery is what happens in between. How do all these motions cross over here to here? That's actually the frontier in ocean mechanics, ocean fluid mechanics, is how does that happen? As Jim notes right here, the Rossby number and the Froude number pass through one going over here, so it gets really big. So it's what happens right in there. And so Jim has been very much interested in what he calls submesoscale motions. Okay, I thought I would just say a few background words, which will get clearer here in a minute. The ocean surface is really spatially heterogeneous, as you'll see in a minute or two, over a broad range of scales. So there are sharp horizontal gradients in buoyancy and currents. So normally, the atmosphere drives the ocean, especially well known at big scales. But once it gets smaller, the ocean can drive the atmosphere. That's shown very clearly by people like Dudley Chelton. If you look at the correlations between wind speed and SST, you see that it gets reversed. So that's an intriguing idea. It impacts the curl and divergence of the wind stress, something that the oceanographers are really interested in. Over time, Jim has developed ROMs. It's a little bit like WRF. They have multiple levels of grid nesting. And so they can look at scales between here and here. They keep pushing it to even smaller. They would love for it to be a non-hydrostatic code, but it just won't do that. But that's the range they look at. It ends up that people have been interested in this regime, so they've coupled WRF and ROMs together, looking at mesoscale motions. But they have 1D column models for boundary layer mixing. A young fellow at Woods Hole has such a model. One of Jim's postdocs, Renaud, he's written a whole set of papers on this kind of style coupling. One of the things that they find is once you include the currents in these coupled models, they coined the term eddy killing. It reduces the strength of the eddies in the water. So it impacts the ocean really to a great degree. If you'd like this topic at all, Jordan Small up at CGD wrote a review article in 2008. It's pretty nice. They kind of looked at mesoscale kinds of things. One of the things they conclude, boundary layer schemes are suspect in these coupled models. Okay, so that provides an opportunity. Maybe LAS can say something interesting about that. Okay, I promised I would show you some pictures of what submesoscale things look like. This is a beautiful one. It was actually taken from space. Scully Powert's very famous picture. And you see this scum lines, and it forms this vortex street. There's order 10 kilometers there. It's prolific at the ocean surface. It says something really interesting happens at these small scales before it goes down to the boundary layer. The scum lines get really tight, lots of convergence, beautiful fluid mechanics. Here's another one. I've shown it before. It ends up that plankton, those kinds of things are great tracers in the water to look at complexity. And that's surely complexity in the ocean. This is about 10 kilometers. You can zoom in. There's a kilometer. I asked Jim, what's going on? He says, I don't know. If you look at from space again, here's the Gulf Stream. Okay, lots of change in SST. You start to see some gradients, but not enough resolution to see all the fine detail. The one on the right is a really nice picture. It's a SAR image. Okay, and you see all these black lines. It's a two-step process. There's lots of scum at the top of the water, okay, other kinds of things. When it gets squished into fine lines, it damps the capillary waves and the short waves that actually carry the wind stress. So in an instrument like SAR, that turns into a black line. Okay, so these are all convergent lines, filaments, vortices, all kinds of things. Some of them are actually Langmuir turbulence, but it's pretty long. Okay. Okay, so Jim turns on ROMs, okay? Lots of nested grids, lots of helpers, doing lots of work. So here's the Gulf Stream again. They put a nested grid right around this temperature filament right there. They zoomed in enough. There's a cold, dense filament there. Same kind of thing here, here, okay? So there's lots of structure at small scales. And finally, Jonathan Gula made this fabulous picture on the right. That's vertical vorticity normalized by F, okay? And it's a sub-mesoscale soup. Okay, so with that little bit of introduction, sub-mesoscale ocean turbulence fills the boundary layer. I mean, the mesoscale and the boundary layer in the ocean. All kinds of structures, filaments, fronts, vortices. We just asked a simple thing. This could have a yes or a no answer. Do atmospheric boundary layers respond to gradients in SST and currents? It's just a simple science question. We're going to do really big LES, idealized process studies. There's no machine alive that will compute all the turbulence in the atmosphere sitting over a water body like that. Not yet, anyways. This might be a typical spacing in the air, and that's in the water. We have lots of words. Okay. We talked a little bit. We want to look at horizontal heterogeneity. But I have a Fourier code. It's got periodic sidewalls. When the stuff flows out on the right, circles back in, comes in from the left side. Don't want what comes out to contaminate what goes in. Wanted to do something about it. I called it, what I put together, a Fourier fringe scheme, okay? It's Fourier because the basis functions in the LES are Fourier series. So, basic idea, real kind of clean. We're gonna run two LES at the same time. One in a relatively small box, and you would consider those answers good, okay, if you just looked at that by itself. Then we have a big box, H, and we're gonna put some heterogeneity in there. Could be roughness, it could be temperature gradients, all kinds of things, okay? But when the flow on the right-hand side comes back in, we're gonna intercept it, and we're gonna nudge the answers right here with this nudging function so that this in the P domain ends up here and then gets transported across there. Okay, this is actually an engineering idea. We just kind of stole it and modified it a little bit. So, some nice things. Automatic generation of the inflow and outflow conditions. The inflow turbulence is real turbulence. It's not random phase. Okay, we don't have special inflow-outflow equations. Leaves all the basis functions alone. You can do this really nice with MBI. When the code starts, let's say you're running with 2,000 processors, you say, oh, 200 processors do this, 1,800 do that, okay? Runs through exactly the same equations. Okay, so they're simultaneous, they share delta T and delta X. Okay, does it work? Okay, so here's just an example, close to the water surface. Here's what's in P, okay? Here's what's going on in the fringe. Here it runs out. Okay, so you can see right here, this is from the far right-hand side. I'm just showing a fraction of the H domain, okay? So runs out, we nudge it hard. This starts to inherit the turbulence in this domain. Okay, averaged in this red box, those are the mean profiles. The circles are the H domain. The lines are the P domain. So the mean profiles are really good. Does really good for the turbulence too, okay? Same kind of thing. So it really works. Okay, so that leads us to our first set of little examples. We're going to do LES with thermal heterogeneity. Real simple problem. I apologize. I love pointing at it, and I want to go over there. Imagine, I'm going to call this a cross-front winds. Imagine the geostrophic wind is blowing left to right. Here's a heterogeneous change in the temperature. Could vary L. That could be plus theta, minus theta. Okay, set of experiments that look like that. Really big boxes, 7,680 points in X. Okay, so want to make sure the domain's really long to watch what happens. A neat twist on the problem is you simply take the geostrophic wind, blow it into the board. So that's a VG, same magnitude as that. If you remember your EKMAN dynamics, surface layer winds turn, so there's going to be a U that goes this way. Same setup, though. All right. Okay. Just what happens? Okay. So here's a jump. It's going from a warm surface to a cold surface. Okay. It's crossing right at this line. Shows really nice this transition to stable turbulence. The other thing you notice, really takes a long time, really big distance. Okay, a couple weeks ago, EKMAN from RISO, in the bottom, it's just the opposite. This is warm, this is warmer. We're looking at vertical velocity at about 41 meters, okay? A couple weeks ago, Jakob talked a lot about large scales in the atmospheric boundary layer that he actually measured. Well, these W signatures, we see them all the time, are actually signatures of that. These, it's really nice. These are the updrafts from the big cells turning over, coming up, slow downdrafts. You actually see the lines merge together. It's really, really quite neat. There's holes in the turbulence here when it goes to a stable case. All right, and then it runs out the end. The other thing you notice, none of that stuff on the right shows up on the left. This is geostrophic winds 10 meters a second. Okay. Okay, I'm going to populate this slide with 4 panels, just some simple statistics for the case where it goes from warm to warmer. Okay. The first thing, here's the front. Okay, there's downstream. So I've taken the wind, the horizontal wind, subtracted the upstream average, so that's the anomaly. So you see really nice, this is warmer, okay, grows, grows, grows. The vectors actually turn here, there's actually downflow right here, okay, grows into the boundary layer, slows down, really nice. Okay, so I'm looking for statistics that show that this jump actually does something. So it ends up that this is a neat metric. Okay, so in a normal boundary layer, like I've drawn there, there's a certain place, in a convective case, there's a certain place where this goes through 0. Down here it's negative, up here it's positive. So what this little band shows, right here, okay, that's the region where the boundary layer transitions from being negative to being positive. Well, this is a really neat overshoot, not monotonic. Jeff had a really good name. It's super adiabatic down here, okay? The surface layer warms up much more quickly than the top part, and you end up with this really neat overshoot. So, didn't expect that, just what had happened. If you compute vertical velocity variance, same thing, compute statistics at each x, average in time, normally there's a peak in the vertical variance. It makes a peak, but it's not down at the end of the box, it's in the middle somewhere, and that correlates well with this overshoot. Finally, if we look at something exotic like d by dz of w prime theta prime, you can see it lift off and hit the inversion, come down, complicated flow. So the whole purpose is the statistics are not monotonic when it goes through a simple SST jump. Okay? Okay. One of the important things, what do the temperature fluxes look like? What does W prime theta prime look like? Going from warm to warmer. Okay, so the front is about right here somewhere. Okay, so you see that overshoot again, and then you see a smooth transition. These colored bullets, red, green, blue, purple, orange, blue, and black, I've plotted single column profiles down here that correspond to these colors. So this red one is right here, and that's far upstream. So you see the classic shape. Okay, it's a little less than 0.2, everything's good, goes to 1, and then you can see how quickly the surface layer transitions as we go downstream. But this blue one right here is right in the middle here. It even overshoots what's over here at the black one. So super adiabatic, we end up with this non-monotonic transition as we're going across there. Really neat. Okay, so you do the experiment from warm to cold, shown over there on the right. Same kind of thing. Here's the far upstream profile, and then as we cross across, surface layer responds almost instantly, and then there's a lag. This blue one right down here does the same kind of funny transition, and then the black line, even down there, is still not what you would consider statistically stationary. Okay, oops. I wanted to say something about secondary circulations. There are secondary circulations in the previous case with across-front winds, but this one's kind of nice. Like I said, the geostrophic wind is into the board, so down at the surface it makes a U to the left. Okay, so here's an example. It's warm to cool. The V is into the page. Here's U, here's W. Well, it's really interesting to look at that U over there. Okay. It's actually going backwards once we cross. So the U is nearly enough to actually cancel the wind from the ageostrophic part. And it forms this layer right up here. Flux is a lot bigger here than it is at the ground. Here's W, see the plumes dying? Okay, if you take images like that and you average, you get this picture. Here's the SST jump. Okay, the wind's going backwards, so we end up with this closed circulation right there. Okay, do the same thing for a warm front. As you would expect, it turns this way, but it didn't quite close. You can get exotic, and you can put in a filament, something where it jumps here, goes up warm, then down. We end up with double circulations inside the boundary layer. So, okay, I think we're okay. I wanted to show the difference in a percentage way, what happens to the surface fluxes, momentum fluxes. So there's two components. So that plot, I've taken the component in the, that's aligned with the ageostrophic wind and normalized it by its upstream value, and the same thing for the one aligned with the geostrophic wind. So they're ratios. Okay, there's far upstream. Okay, these are the ones when it's across front, and here is when it's along front. Okay, so what you notice immediately is, the along front wind, not intuitively, changes the surface fluxes the most in a percentage way. Okay, so, okay, if we look at it from we stand up and we say, okay, what's the difference between those two cases? Between the front blowing across the isotherms or when it's blowing down the isotherms? They have the same SST. Well, our friend EKMAN is the culprit. When the winds are blowing across the filament, it's that component is really big. There's U with the across front winds, okay? When when the geostrophic wind is blowing down the isotherms, okay, the geostrophic component is really small. There's almost a factor of 10 difference between that wind speed and that wind speed that blows across the SST isotherms. So what it really tells you, in the case with across front winds, advection, horizontal advection dominates the balance if you look at the momentum balance. In the other case, pressure gradient springs to life and it participates in the balance really well. So the moral of the story is the atmospheric response really depends on what the geostrophic wind is, how it's aligned with the SST isotherms. Okay, and it affects everything. Surface fluxes, vertical fluxes, secondary circulations, etc. Okay. When you work with Jim, he does not leave any stone unturned. What about current coupling? We have to say something about the currents. Do they do anything? And I'm going, do we have to say something about that? He says, yes, we have to say something about the currents, whether they do anything interesting. Push, push, push. This is really an example of using LES as an experimental tool to look around. Okay, so we do what Jim said. There's an LES box. We're going to put an ocean eddy at the very bottom as a boundary condition. Well, a circular eddy is really nice because then it's independent of what the wind direction is going to do. So here's a whole set of details about the LES setup. Okay, this eddy vortex is solid body rotation and it's damp. I'll show you a picture in just a second. Maximum current's a meter per second. We looked at eddies, cyclonic, anticyclonic. We looked at atmospheric stability from real convective to neutral. That's 18 different LES plus more. So we wandered around a lot. And we use, we'll say more about this. We use rough wall coupling with the water. Okay. It ends up that this is pretty important in the whole setup. Here's just a contour plot of what the eddy looks like, real super smooth. This little white band, that's where the maximum eddy speed is. Okay, so it does this. Goes up, hits a peak, solid body rotation, and then it damps down. This magic number ends up being kind of important. Okay. All right. So you do that in a really big box, 37 kilometers on a side, okay. The ZI is, 600 meters or so. This is at 530. The radius of the eddy is 4 kilometers. So this mesoscale sort of effect in terms of ZI, it's way bigger than the boundary layer scale. So this is a really nice picture, just vertical velocity at the top. And you see all this neat structure here, okay, and then you see something else right there, okay. I didn't, not to poke fun, here's Chinho and John's LES box in 1985. And this, it's about right there. So they looked at all these convective plumes that don't have any heterogeneity impact at all. So our box is 7.5 times as big, and the resolution is 4 times finer than what they have. Okay, no one knew that would ever happen. Okay, so this is really interesting. Let's put a little box around here and zoom in and see what we see. These are all classic overshooting plumes with downdrafts on the side, weak downdrafts on the side as they hit the inversion. All right. So, same picture. I haven't changed the color bar at all. Zoomed in at 6 kilometers on the side. This is at 12 meters. So you start to see the hexagon pattern, okay, with weak downdrafts in the interior. If we go up just a little bit, now we're at 24. Now the pattern really starts to pop out. Still can't see anything terribly. Okay, so now it's really powerful. We're at 80 meters. Okay, and the hexagon pattern is we're still centered right on that interesting feature. So now if we go up to 244, here's a ring of convection right around here. Okay, that's a pretty big region of downdraft. So if we put a scale on that, that's about maybe 4 or 5 kilometers where the air is all going down. All right. Finally, if we go up to where I showed it, this is 530. Now it's really clear. There's this ring around it, okay, with a downdraft in the center. You can't leave something like that alone. Okay, and if you go all the way to the top, you can still see that ring. Okay, when something that neat happens, you gotta ask, what happened? Okay, so took the LES data, all right, so the eddy's spinning beneath it. Okay, we zoomed in this and converted all my Cartesian velocities, okay, into r theta. So this is the radial component of the velocity. Okay, there's the tangential component. Here's the maximum radius, the maximum radius that we use to scale everything by. It's this black ring. Well, okay, there's just a small movie of what is happening to the radial velocity. We're close to the ground, okay, 10 meters. If your eye's quick, all of a sudden you go, wow, change of sign right here. See, all these blues are negative, all these yellows are positive. So right in the inside, it's going this way, and then on the outside, it's going that way, okay? Here's the tangential velocity. You can see the rotation that it's induced on the convection. It's going around, special stuff happens on the inside. That's the tangential component. We can blame Rich for this. About a year ago, Rich gave this fabulous talk. He was going somewhere for a meeting, and he wanted to talk about secondary circulations in a rotating boundary layer. Okay, nice talk, great. So he invoked this image from Schlichting's book, okay, where the bottom is spinning. They develop an analytic solution. Okay, if you notice anything about it, the analytic solution says it's got to be down and then out. Where you remember I said our tangential velocities were special. It had a peak. Lo and behold, that's pretty much where the peak in the in the tangential speed happens. So this is really cool. It has Schlichting's answer in the interior, but we have convection on the outside, and so it does two things.
Blame von Karman. That's von Karman's solution.
Okay, but it's really neat. So we've done a problem that has that sort of character to it. It's convective turbulence that wants to suck the air in, but in the center wants to push the air out, and it pushes down at the same time. Oh, I just thought that was so neat. Okay, here's the surface fluxes. Here's the temperature flux, okay, that's at the bottom of that eddy. Those are the momentum fluxes in polar coordinates. And sure enough, if you look at the tau r, the one that points this way, changes sign right there, okay? But what happened here? I ran this problem with constant SST. What happened? Neat. But it has this very swirly character to it. Really neat. We're actually looking at the anomaly, so it's the difference. So that's a 80% one way and minus 80% the other way. So what happened? Okay. We'll get to that in a minute. Let's look at some other things. So here's the pressure in that flow, okay? really low pressure in the center, and we saw that the secondary circulation went this way. Reverses if we turn it around and make it be anticyclonic. That's an XY plane. You notice it's really big. That's why I made the box so big. But if we look in the an XZ plane, so here's the pressure again. So comes up, splats against the inversion, turns around, then goes up. The other side does the opposite. This is down, right there in the inside. So there's a sort of a ring updraft surrounding that convective eddy. Okay, given all that, nice flow viz, make some statistics. We take our answers in Cartesian space, interpolate like madmen into r theta coordinates, and we just plot it as a function of r. So here's the momentum fluxes at the surface, and here's the temperature flux. So sure enough, becomes negative, overshoots as the air starts to blow in, becomes positive, and then smoothly decays, right? Told you it was constant SST. There's a 40% change in the surface flux. Those are the winds over there on the right. The interesting one to look at is W. That's the blue line. Okay, there's 10 meters, not much W. Go up a little higher, there's some W. It's down in the center and then reaches a peak on the outside, right where the eddy changes sign, where the motion changes sign. Okay, if we go to 242, down, shoots up. Okay, notice what happens when it gets really close to the inversion. This is the radial wind speed. It's in, then it changes sign and becomes positive. Okay, right at the inversion, makes a big splat against the top, pushes all the air sideways, and it changes sign. Really nice. Okay, the turbulence knows that this happened. These are the variances, same kind of thing. Right here's where all the interesting things happened. Here's the variance in the radial direction. That's the variance. The green line is the variance in the tangential direction, and blue is W squared. Close to the boundary, not much. But if we go up, oops, okay, there's 22. There's about 40% through the boundary layer. Okay, so it's scaled with W star squared upstream. So we see a real neat peak in the variance. Okay, that's almost the classical answer. It's about when W squared over W star squared, it goes to about 0.3, 0.35 or so in a regular homogeneous boundary layer. But right there where all this happens, we see this neat imprint from the ocean eddy on it. Okay, so how did all this happen? Okay, hopefully I can explain this using just a few words. Here's the computational stencil in the LES. Here's the first grid level, there's the second grid level. We put the U's and staggered all at the center. That one's at the center, okay. Here's the water surface. Okay, so there's the equation, the bulk equation for the taus. It's got delta U in it. It's U at that point minus the eddy speed. That's delta U. Well, that's what tau looks like. Oh, the bulk rule for temperature flux has also got a delta U in it. That's where the coupling comes from. So if we look at the transport equations at that first point, all these red things are boundary condition terms. So you can see once we put it in theta, right here, et cetera, it can propagate into the pressure, and that's why it feels it all over. Okay, so didn't appreciate it before I ran, but it's obvious now that's what happened. Okay, let's turn on the winds a little bit. Okay, so it's convection plus winds. It's Rich's rotating boundary layer plus wind. Okay, I'm going to define these surface flux anomalies like this. It's just the tau at that spot, averaged in time, normalized by u star squared, way far away, -1, so this ends up being a percentage. Same kind of thing for the temperature flux. Whoops. Okay, so you make that plot. Here's the momentum flux distribution. We turned on the winds. Well, when it was free convection, we just saw this really big circle. What happened? This means that this is 50% larger tau, and this is 50% lower than the free stream value. This is really big. This is with an eddy of 2 kilometers. So that's nearly a kilometer on each side around. So the eddy really had a big impact on the taus. What happened? Well, pretty easy. Okay, if the surface winds are blowing this way and the eddy is rotating that way, the currents over here are opposed to the wind. So imagine the air is blowing this way, the currents are trying to pull it back. We generate a lot of momentum stress. On the other side, the currents are aligned with the wind. So wind's going the surface stress going this way, so the current's pulled up, and so there's not as much. So the currents introduced this neat dipole pattern just because of that. Those are pretty big changes in the taus. Well, because of the coupling, okay, I talked about before, it also makes a temperature flux dipole. It's hotter here, cooler there, not as much heat flux. Okay, I went quick, okay, but the winds are blowing this way, so that this ends up being like my along-front wind case. So the potential secondary circulations are in this plane right here. Okay. Now there's not many directions. There's not many directions to average over. Pretty much all you've got is time, and maybe you can do a little bit of X or something, you know, but hard to get statistics. Okay, so imagine we're over here and we look this way, okay, down from the Y direction, and we ask, what does the PBL see? Here it is. Okay, these are the average eddy-induced motions in a weakly convective one where the radius is 4 kilometers. Okay, so right away, okay, the temperature feels it at a really big scale. Okay, these are the anomalies like I defined previously. It's cooler here, it's warmer here on that side because of the coupling with the currents. Okay, goes up, creates this anti-pattern, the pressure sees it too. Okay, if you look at the span-wise velocity then, this gradient in P right here drives this. Okay, it's hard to get W, but there's a positive W goes up. Once again, the gradients down here drive it the other way, goes here. Right here it's down. Okay, so we end up with this circulation that looks like that. Not terribly large, but it's definitely there. Okay, if we just simply reverse the sign of the eddy underneath, the pattern is just reserved. So it's clearly an eddy effect. Just to convince myself that I didn't mess up, turned off the eddy, just ran the case with nothing. So there's no anomaly in the pressure, the temperature, or the span-wise velocity. These are the signatures of the shear convective rolls that one gets always when you have that style mixed boundary layer. So the anomalies are definitely due to the eddy. Okay. I told you we cooked up this fringe scheme. So here it is applied. We're looking in the XY plane. Here's the eddy close to the surface. Okay. It's not circular because I had to distort the aspect ratio of the plot. Okay, but there's the eddy. It's cyclonic, so makes this neat temperature wake. It's not terribly strong, but it clearly makes this temperature wake even at the top of the boundary layer. You can see it. Okay. If you take a cut right at this dotted line and you look in the YZ plane, sure enough, you follow the streamlines and you get something that rotates in that direction in the atmosphere. Okay. That was the tour. So, just a few thoughts. Spatial heterogeneity at the ocean surface is ubiquitous. It's everywhere in the ocean. It's that kind of range. In order to see those effects in the atmosphere, you need large LES domains with fine grid if you want the turbulence. Lots of grid. Okay. That thing works really well. The atmospheric response depends on the orientation between the surface layer winds and the SST front. So when the when the winds are parallel to the large-scale winds are parallel to the SST isotherms, pressure gradients are really important. In the other case, where it's across, the advection is the dominant player. And those SST fronts, if you look hard, you can see them in all those kinds of things. Okay. What about the eddy? Surprisingly, we found that currents introduce both mechanical and thermodynamical heterogeneity. It's both in the momentum fields and the temperature field. Depends on the stratification. You turn on the winds, you get this really interesting dipole pattern that scales with the radius of the eddy, even with constant SST. In fact, if you use just constant surface flux, that neat interaction disappears. So the one we're specifying SST actually generates the heterogeneity. Okay, so this isolated eddy leaves this coherent wake in the ABL. Hard to see, but it's definitely there. These flux rules better be right. They better be right. The Jim Edsons and the Chris Farrells of the world, those things better be right, otherwise it doesn't mean anything, okay? It's interesting, Jim cooked up a EKMAN-style model, no heat flux or anything. He solved classic EKMAN equations with constant viscosity, but he put in these rules at the bottom, and boy, he gets that beautiful dipole pattern just like LES. So these better be right. There's a whole bunch of questions one could ask. What do the waves do when you have this? Okay, maybe a M³ topic, too hard? Are there links between the heterogeneity and the clouds? If you have this sort of complexity at the water surface, there are teleconnections to those marine or those tropical clouds. Maybe, maybe not, but you won't know until you try. So it just posed, do we need more atmospheric OBL coupling? Hey, thanks for listening. I'll stop there.
Paper's open for questions, comments. George?
Yeah, you kind of stole my thunder there. I was going to ask you how confident you were in your lower boundary condition. Because I remember the Sea Blast BAMS article. You know, they retrieved C sub H from observations, and it was all over the place. And I guess one of the hypotheses was it's the impact of the currents that changed the effective conditions. So I guess what did you just use a constant, I presume, for?
No, we
CD
actually go through the MO rules at point by point, so it gives a variable CD and a variable CH depending on what the stability is. We just need to know that stuff. George's comment about CH is really interesting. See, this when you have a real rough surface is determined by the pressure. I mean, it's the form drag around all the elements that gives you that. I mean, this guy, no. It's the actual heat transfer from the surface. So once it gets really rough, these guys kind of ended up disconnected from which piece of the fluid mechanics actually makes drag versus temperature flux.
Very nice talk, Peter. And because I'm doing tropical cyclone and moist convection, I'm really interested in whether there could be a way for the oceanic eddies movement to couple with the atmospheric eddy movement. Because in some idealized simulations, we saw some mesoscale convective system, for example, they can spontaneously form in a domain, and they will slowly move, and finally some of them will become tropical cyclone. And I think their movement is also slow because it's a vortex cluster. And for the oceanic eddy, it's also slow. So could there be a possible coupling between this?
We need to know how that works. But a first thing that you could do, if you were just interested in the atmospheric part, is to happen to have simple 1D column models in the water. Okay, my oceanographer friends, Jim Price, etc., they think they know how the water responds really well to that. And they actually take the stresses and put it there, and it ends up that the notion of inertial rotation, the tau is rotating into the currents, wow, makes it mix really deep, leaves this really neat oscillating structure in the water. Complicated stuff, you can speculate, but you need to do the experiments.
I see. Thank you very much. Thank you.
Okay, other questions, comments? Morris?
This may be a really silly question.
Since
I don't know anything about this stuff. But it seems like, the assumption in a lot of what you're doing there is that the flow is geostrophic, and which constrains the boundary layer in a certain way. What if the flow isn't geostrophic?
We got more parameters in the problem, Morris. It just, the complexity is high. It just, the potential to do exotic things is just laying there out there.
Yeah, because it seems like, for example, most of the oceans are where Coriolis force is very weak, right? So.
Yeah, no, it's, that's why Jim has been so interested in this connection between submesoscale kind of turbulence in the water, what it does to the atmosphere, do they talk back and forth? It's kind of the frontier in this field.
Oh, Jimmy. Race across here. I gotta get on a track.
Yeah, I've looked a little at the waves, how they affect CD, and you can represent it as a linear function that increases, it doubles basically by the time you get to 20 meters a second.
Yeah.
So that could be an easy thing to add to this
Yeah,
model. I'm not sure, but it probably at the 5 to 10 meter a second range, it isn't doing a lot in percentage-wise, but.
Yeah, a nice thing to do would be in this kind of coupling scenario is make Z naught on one side something tied to the winds, make Z naught on the other side tied to the winds. So there would naturally be a momentum jump, with SST gradients or just, the waves are going to change, drag's going to change. Yeah.
All right, so we have a question here from Hugh Morrison. What scale do you think that cool ring convection pattern with descent throughout the center in the free convection case would break down? I think the ratio of ocean eddy to PBL size, PBL depth was something like 5-to-1 or 10-to-1 in that run, question mark. As it gets smaller or larger?
Nice question, Hugh. So one of the calculations we did in that free convection run is to make the solid body rotation really a small piece of the whole problem. then you don't, there's just a tiny downdraft in the center. So then it disappears. If you make it bigger, one of the reviewers of the paper said, I want a 20-kilometer eddy. Well, it's gonna do that. It's just having enough horsepower to actually see it. I'm quite sure in the free convection case, when I did 4, if you double or triple it, it's gonna get even more. It's just gonna grow. Because of Rich's Schlichting argument.
So let me ask one last question here. I was interested, how do you piece some of these mechanisms together to get to the eddy killing?
Oh, okay. I have a plot, but what happens in the water part, you look at the, let me see if I use the right word, the wind coupling term and the interaction. The plot is really pretty dramatic in that it creates a very large pool of negative energy transfer, and whereas it's pretty weak going down, so that weakens the whole system. It could be 20 or 25% eddy killing. I know I didn't explain it well enough for you, but I could definitely point you to where that happens. If you look at the same mechanism in the atmosphere, you see it, but the amplitudes aren't changed. It just rearranges where it's set up. So in that regard, the ocean's much more a slave to what the atmosphere is doing.
All right, well, thanks again, Peter.
All right. Hey, thanks.